We're going to continue on with the concept of limits. And we're going to dive more in depth into how to find limits. Staying with the process that we had from last week, that was plug and chug, algebraically manipulate, plug and chug again, pray, cry, all those other variations we had in there. We're going to start going a little bit more in depth to make your life a little bit easier. We're going to use some limit laws. These are so obvious that you probably didn't even think of them. And they're so obvious, we're not even going to use them. You'll understand what I mean when we get there. We're going to plug and chug again, because plugging and chugging makes your life really easy. We're going to algebraically manipulate, so we might refresh things like factoring the difference of perfect squares, factoring the difference of perfect cubes like we talked about last week. Oh, we'll factor out some common terms, all kinds of fun stuff like that. Then we're going to review left-hand limit equaling right-hand limit and why that is importante for limits. Then we're going to learn the squeeze theorem. That would be the point when some of you are going to need some Kleenex. Also known as the sandwich theorem, also known as the pinching theorem. We'll save that for last. And then today, you just got to relax. Okay? Whether you want to or not. Any questions? No? Great. Okay. Hey, I got a new mother function for you. There it is. Absolute value of x over x. Just like the other mother functions, we can base all kinds of functions off of that guy. So for instance, you could do the absolute value of x minus 4 over the quantity x minus 4. That would be another function. It's just that guy moved to the right or left? Right. To the right 4 units. Good. But there's the graph. Okay, so why are there open circles at 0? That's a redundant question because I'm guessing you understand that 0 over 0 still doesn't work for us, and it won't for a long time. And then if you take any other value of x and put it in there, you're going to end up with 1. Or negative 1, depending on whether or not you put in a positive or a negative value. Okay, so everybody's good with the graph, yes? And he knows.
Thank you.
You're welcome. Okay, so what's the limit equal to? This is awkward. Somebody's gonna ask?
It doesn't exist.
Why?
Because they're not the same. Limit. How do you say it? Limit x minus x. How do you say it? Is that word basically?
Well, you use your words and then I'll use some symbols.
The negative limit of x is not the same as the positive.
Close enough. Okay. Left-hand limit doesn't match the right-hand
Right,
limit.
that's the way.
As I mentioned, that's a new mother function. I don't remember what I have here. There we go. Okay. Now, why is that there? If we go over here, click, click, click. What's the limit as x approaches 0 from the positive of the absolute value of x over x? 1. Everybody good? Beautiful. What's the limit as x approaches 0 from the negative side? Negative 1. And last time I checked, negative 1 does not equal 1. So therefore, this guy right here does not exist. Make sense? Yes. Beautiful. Let's move on, shall we? But again, that'll pop up a lot. Properties, I'm going to go through this quickly because you're not really going to use this, but this is the pure math and associate. This is what allows us to plug and chug. Okay, that's the simplest way to put it. So let's start with number 1. Why is the answer to number 1 just plain old B? Now, what do you need to know? You need to know that C is a number and B is a number. They're not variables. Why is the limit of some number when x approaches a different number equal to B? Outstanding. At where? Good. That function, b, is a horizontal line at b. It doesn't matter where you choose an x value, the y value, which is what a limit is, will always be that same value. Okay? Tick. Well done, thank you very much. Y is the limit as x approaches c of x equal to c. Come on, you're better than this. I'm not telling you. Are you raising your hand or are you just fixing your hair? Go.
Cause you like the C for X.
That's one way to look at it, yeah. You just plug in c for x and you get c. What's the graph of y equals x look like? Yeah, use your words.
Like,
Because that's not going to make a lot of sense on the video.
just like a diagonal line,
What kind of diagonal line? Be more specific.
like with a slope of 1 to 1,
Excellent. Passing through the y-intercept of.
0, 0.
So what's true about any point on that line?
It's 1 to 1.
Keep going. If x is 2, what's y?
2,
If x is negative a gabillion, what's y?
negative gabillion.
Good. So the x and y coordinates are the same, yes?
Mhm.
So no matter what x value I put in there, I'm going to get the same y value. Two different ways to approach the same problem. Hot diggity. Okay. Or just plug and chug. And then the last one is also just plug and chug. An exponential function. And n can be any number. Okay. Beautiful. Now things get a little crazy. We'll do this quickly. Wow, there's a lot going on there. Don't write it. Don't write any of this down, because I'm just going to give you the shortened version, and you're going to quickly realize we don't even care about it. Number one, the limit of a sum is the sum of the limits. You did this when you did some other stuff in the world, like sometimes logs and that kind of stuff. Okay, the limit of the sum is the sum of the limits. The difference, the limit of a difference is the difference of the limits. You can break it into pieces. If you multiply it by a constant, just move the constant out in front, it doesn't affect that. C refers to a constant, some number. And the hits just keep on happening. The limit of a product is the product of the limit. The limit of a quotient is the quotient of the limits. So if you don't know how to take the limit of f over g, then take the limit of f and divide it by the limit of g. And then they throw that calculus stuff in there that says assuming that g of x is not equal to 0. Okay? Now, again, that's the stuff that allows us to plug and chug. Here's my example. Suppose I asked you to do this. Find the limit as x approaches 2 of that quadratic, 4x squared plus 3. So, don't write this down either. Just wait. Be sponges. Absorb. According to the limit laws, the limit of a sum is the sum of the limits. So I split that into two different limits. That's legal. Then I factored out a 4 because the limit of a constant times a function is the same thing as a constant times the limit of the function. Then I took some limits. The first limit of x squared was, I think, version 3 on that slide. And the limit of 3, I think, was version 1 on that slide. Okay. And I get my answer, which is 19, right? 4 times 4, 16 plus 3, 19? 19. Good at math. Which is ridiculous. We're never going to do that again. What we're going to do is just plug and chug. Rule number 1, plug and chug. Plug in 2. If I plug in 2, does anything weird happen? No, I get 19. Done. But, so the question is then, why did I do this? Because I think it's important that you understand what allows you to do this. There is no plug and chug theorem in calculus. It actually comes from all these different limit laws. Good? Problems? No? Great, moving on. Go ahead, find that one, I'll wait. Yeah, everybody's here, huh? When you get an answer, check with your table to make sure you're on the same page, or if you're the odd person out, or if your table's all crazy, or what do you got going on there?
I don't think it is DNA because one plug and chug. 1, 0. 1 gets you 5. Negative 1 also.
So 2. Yeah, what? Step 3. So you agree that 0 exists? We might have to have cable battles on getting different answers. All right, hold Interesting. We have a discrepancy amongst the room. What does stuff have for an answer? 6.
What am I doing?
That's half. Okay, so let's come to that. Talks about attentive. Sorry, I just lost the ability to speak English. There is some discrepancy in answers. Some tables have does not exist. Where are you at? Okay, interesting. Some tables have 6. Where are you at? And then we got a couple outliers, like I think somebody fired off a -6. Okay, what's the right answer?
If you divide it by 0, it's does, and it the k is 0 and k is on the bottom, so it doesn't exist no matter what is on top.
Let us review, shall we? What, May?
Well, I was just
Did you
gonna
want to fight?
Well, don't you have to take the limit of both sides into
Top and bottom? By sides you mean top and bottom?
I don't know. I just took I took the whole equation and I did limit of k approaching 0 from the left and then 0 from the right.
Stand up, sit down, 5, 5, 5.
It doesn't say coming from the left.
Yeah, it doesn't say coming from left or right.
It
But
just-
can't you find the limit by doing both sides?
You can, but you don't have to, because the only time you have to worry about left and right is when there could be some oddity there. So let's go back to the basic rules. Step number 1 is what? Plug and chug. And do we all agree that if you plug 0 in for k, you get 0 over 0?
Yes.
Okay, good. Which would be the reason why some of you, I'm guessing, said DNE. However, what's step 2? You guys get a comment to
So you got it right.
algebraically manipulate. How do I algebraically manipulate this bad boy? Let's go with blue. By the way, as you algebraically manipulate, you're going to get lazy and not write the limit. You have to write the limit every time. Posey, what's 3 plus k quantity squared?
K squared plus 6k plus 9.
K squared plus 6k plus 9 minus 9 all over k. Let me come back to you, Posey. Did you do that? Did you FOIL that? Or how'd you get this? How'd you multiply that out so quickly?
I did it in my head.
Oh, very nice. Square the first term, multiply 2 together, double square the last term?
Yeah.
Respect. Okay? 9's cancel because 9 minus 9 is 0. I'm going to be overly picky here. Some of you, while I was walking around, just canceled out those 6's. Sorry, those are k's. Canceled out the k's. Be careful with that. Technically speaking, from a nerd perspective, you're supposed to do this. Okay? However, some of you probably canceled the k's correctly, still got k plus 6. What's step 3? Plug and chug, and we get 6. DNE is kind of an answer. You didn't take the problem far enough, though. Again, remembering those 3 steps. Plug and chug, algebraically manipulate, plug and chug again. Now, it would be nice if every function that we look at when we take a limit is going to fit into that nice little category. It won't. So let's look at some different examples. Got that? Okay. We talked about number 1 already. You'll recall when we graphed that on Desmos and saw that it approaches 1, even though we had no explanation. And then number 2 is the second big trig one. I wish I had some clever way to help you memorize this. And again, as I mentioned the other day, I'm not a big fan of memorization, but at some point in here, you're just going to have to memorize it. The term flashcard worthy, I use that term all the time, but old school, we used to remember things with flashcards. You would write them on a flashcard to test yourself. You probably have an app for it now, right? Is there a flashcard app? Yeah? Okay. We good? Excellent. Okay, so let's go through the steps again. What's the tangent of 0? What's the tangent of 0? 0, very good. So, step 1, plug and chug. You get 0 over 0. Then what? Excellent. How would I do that? Whoever's talking. Say you may?
Yeah.
Excellent. Okay, step 1. Check. 0 over 0. No good. Nichts sehr gut in German. 2.
Oh. Then you gotta you would do sine over cosine
Over.
x.
Okay, hold on. The limit as x approaches 0 of sine of x over cosine of x over x. Ooh, fractions within fractions. Icky. Now what?
Couldn't you do the limit of sine over cosine and then divide by the limit?
We'd get 0 over 0 again.
Oh, I don't know.
Anybody else? What's next, Lauren? Yeah, that's one way to do it. Okay. So you're suggesting multiplying by cosine over cosine.
Yeah.
Right. Okay. But yes, Liam.
Sorry.
Don't be sorry. Go ahead.
Well, couldn't you also multiply sine x by x?
Interesting. Other ideas? Okay, so let's do it. I'm going to do both. Dividing by a number, same thing as multiplying by the reciprocal. Yes. So this becomes the limit as x approaches 0 of the sine of x over cosine of x times 1 over x, because the reciprocal of x is 1 over x. Hot diggity, I'll come back to that in a second. Let's use green. limit as x approaches 0 of the sine of x over cosine of x all over x times the cosine of x times, or over cosine of x. Is that a legal move? Yeah, why? It's equal to 1, and you can multiply anything by 1, and it doesn't change the value. Waboom, waboom. The limit as x approaches 0 of the sine of x over x times the cosine of x. We're in the same spot. Now what? That's what I was going to say.
Can we split it up as?
Heck yeah, you can. Because the limit of a product is the product of the limits, yes? I'll change colors again, only because I can. Purple. So this would become the limit as x approaches 0. Jessica, how would you split it up?
Sine of x over x times cosine of x.
What's the cosine of 0?
1.
1.
And the other one is secant.
And this we just learned.
1.
1. Last time I checked, 1 times 1 is? Which one of you was that? Was that? Oh, it's okay. I have transfer papers over here. I can fill those up for you later. Not so bad. Same process though, just a little bit more complicated. Plug and chug doesn't work. Algebraically manipulate. This algebraic manipulation was a little nastier, and especially when we're dealing with trig. And then the last thing we did is plugged and chugged again. Put 0 in there. This one we didn't really put in 0. We kind of cheated and used that theorem that we memorized. This one was a true plug and chug because the cosine of 0 is 1. 1 over 1 is 1. Okay. Good. Yep. Okay. Here we go. This is going to be fun.
Theorem.
Now, the good news is that you will seldomly, if ever, have to take this from start to finish. You'll work with pieces of this. But it's a really simple conceptual theorem, in my opinion. And because of the way I explain it, I prefer to call it the sandwich theorem. Okay? Abby, you making a sandwich?
Yeah.
What kind of bread do you like?
Well, like, I like sourdough bread, but it's not like a sandwich bread.
Yeah, it is,
So it's
'cause
like,
you-
that's like.
Well, because I know where we're going, sourdough's a little tough to work with.
Yeah, just plain like white.
Like plain old like Wonder Bread.
Yeah.
Love it. And what's your lunch meat of choice?
Ham.
Excellent. We're making a ham sandwich. Okay? Now, you take your 2 pieces of bread, and we're going to keep it simple. We're going to take 2 pieces of bread and put a piece of ham on it. Right? Sorry, only 1 piece of ham for discussion purposes. Now, Abby likes to smush your sandwiches. So she's going to press the sandwich down. Just smile and nod. Good job. Okay.
Just ham and bread.
Ham and bread, that's it, plain. Just don't look at me in that tone of voice, okay? Just roll. It's an analogy. It's a metaphor, if you will, for the sandwich theorem. Okay? Takes her 2 pieces of bread and she smashes them down, presses down on it. Maybe you're making a panini. Maybe you just like to smash your sandwich. I don't know. It's up to you. I don't want to get into your whole sandwich world here. We're just using a metaphor. Okay? Once she's smashed down her sandwich, you can all visualize the fact that the ham stays between the bread, yes? It doesn't come randomly flying out of the sandwich, it stays between the 2 pieces of bread. We're good? Is that concept difficult? No. Okay, that's it. That's the whole theorem. Let me explain the calculus a little bit. So, here's Abby's sandwich. She's got a purple piece of bread that we're calling sandwich bread H. She's got a green piece of bread we're calling bread F. And she's got her ham, which is called G. She makes her sandwich, and when she makes her sandwich, and when you make a sandwich, the lunch meat always stays between the bread. Otherwise, it's not a sandwich. I don't know what it becomes. It's got to stay between the bread. Okay. So we're establishing the fact that the ham always stays between the bread. G is always between H and F. And then Abby goes crazy and crunches the bread down here and smushes it down really hard. G is still going to be between H and F. Are you with me so far? Okay. Now, notice the piece of bread up on top, the purple one, H. As H approaches A, what's the limit? In other words, what is the limit as X approaches A of H? L, as in llama. We're good? Any problems? Excellent. Now we look at our green piece of bread. What is the limit as X approaches A of the green piece of bread? Sorry, I lied. The F piece of bread. G is the ham. I'm so confused with my own metaphor. Also L. The two pieces of ham are the two pieces of bread are scrunching down and approaching the same number. So where does the ham have to go? Same place. Therefore, by the way, do you know this symbol? 3 dots? Means therefore, as X approaches A of G, it will also be L. Okay, so let's stop for a second before we get into some real math and make sure that you understand the analogy for the bread and the sandwich and the ham. Are we okay with this concept? Okay, now one thing we didn't list that I'll put over here is that G has to be less than H and greater than F for the whole time. The ham can't just go flying out of the sandwich. Why do we care? Well, let's suppose H is a function that we know how to work with. Something really easy, and I have an example in a second, I'll show you. Let's suppose F is a function that's real easy to work with. But G, I can't work with. I can use the squeeze theorem in order to find the limit as you approach some number by finding the limit of the other two functions. Okay, here we go. That's what the theorem says. We did that already. We're good to go. Let's move on. That's a sandwich, by the way. I don't know why I included a picture of salt. But, oh, I know, it's squeezing. That's what it's pinching, yeah, it's pinching. It's a pinch of salt. Okay. So sandwich theorem, I don't have squeeze. I should put a picture of the old 80s band, Squeeze. You wouldn't get that relationship at all, but that's okay, it would make me laugh. Okay, here we go. I got a big scary function. Do me a favor, graph that function on Desmos, please. Not the limit, just the function. X squared times the quantity, sine of 1 over x squared. It's easier to do on Desmos, by the way, not on your calculator. Nice. That's just great. Huh? Okay. This thing is called an oscillating function. It goes up and down and up and down and up and if you're on Desmos, if you zoom in, you'll notice it's the same thing over and over again. No matter what you do, it continues to oscillate up and down and never really approaches a number. You could holy guacamole. What the? You broke it. You just broke all the decimals. Let's try that again. Okay. So even if you could zoom in and get really, really close to 0, you're going to see the exact picture you see now. Okay. And I know some of you don't believe me, so you just keep zooming in, but trust me, it'll continue to happen. Okay? In other words, I can't necessarily see what happens when it gets to 0, so we're going to cheat. and we're gonna build that function. And I'm gonna build that function by starting with, oh, that's what it looks like, by the way. I forgot I included a picture. I'm gonna build that function with this mess. So bear with me on this one, I'm gonna explain what happens. Because I should have done this in stages, I didn't, I just threw it all up there. Okay, you should know by now that the sine function, the largest value of the sine function is 1, the smallest is -1, right? The sine function goes up and down between 1 and -1. And that doesn't matter what it's the sine of. You can put anything inside that function. You could change the t to whatever you want. Regardless of what you put in there, it's still going to oscillate between 1 and -1. So that gets me to step 2. Now, why did I put 1 over x squared in there? Because I looked up on top of the function I'm trying to build, and there's a 1 over x squared in there. So I slapped that in there. Slap in whatever you want. Doesn't matter. Then, I need to take the sine of 1 over x squared and multiply it by x squared. Simple rule of inequalities. You can do whatever you want as long as you do it to all 3 sides of the inequality. Or 2 if you have 2 sides. So I multiplied everything by x squared. When I'm done, I have 3 important pieces of information here. Number 1, I know what the ham is. Okay. I knew what the ham was to start with. The ham's up here, but I had to get to the ham by building it. Then I know what my 2 pieces of bread are. B1, B2. B stands for bread. H, ham. Okay. At that point, I don't care about the ham anymore. I'm going to focus on the bread. And I'm going to focus on the limit as the bread approaches 0. Okay? So what this step does here is it tells us what we needed to know. What we need to know is that we have a sandwich. So the ham is always between the bread. Okay, the ham is less than B1, but it's always greater than B2, so we've got a sandwich. And then I scrunch it down. And so I'm not going to deal with H, I'm going to deal with the bread. Because now I know that the bread is x squared and negative x squared. And I can easily take the limit of those by doing those 2 things. Take the limit of negative x squared, take the limit of x squared. Those are simple plug and chugs. They both equal 0. They both equal 0. Where's the ham go?
0.
0. Done. Now I will tell you, most of the problems that I've seen involving the squeeze theorem frequently involve trig functions, and you build that trig function in the same way I did it. If it's cosine, for instance, you know cosine goes between 1 and -1. It's usually sine and cosine because they have some nice restrictions there. At this stage, I'm more concerned about you understanding the concept of the squeeze theorem, or the sandwich theorem, or the pinching theorem, whatever you want to call it. Okay, questions about any of that? We're good? Going once, going twice. Okay, we're done. Does that apply to anybody? No. Hit the clear button 5 times. Good. Okay, let's turn this off. Come over here, get rid of this. Come over here. Get out of here. Shoot up. And then stop this.